Hi, this is Chase Shalosky, and this is a video explaining my group's MAT 213 project. So for our project, what we're going to do is we're going to try to calculate how far a bullet is going to penetrate a material based on that material's properties. So after we fire into the material, we're going to cut it in half with a bandsaw. Then we'll be able to confirm our calculations. There's plenty of information online to help us figure out how we're going to do this. So now that we have that covered, now what we have to figure out is which bullet we're going to use for our experiment. There are a lot of different kinds to choose from. However, we're going to go with the 223. The reason is I have a reloading station at home, and along with it, a reloading handbook. Within the handbook, there are several tables that explain the velocity that you can expect from the muzzle from the different powders and how much of each powder. And here are the calculations that we decided to use. We have x equals the mass of the projectile over the area of the projectile times the projectile's velocity squared over 2 times the cavity strength. And we read further and we found that we were able to substitute the cavity strength for 3 times the yield strength. The 5 materials that we decided to test were the following: UHMW, which is a type of machinable plastic, hard rubber, pine wood, carbon steel, and then also stainless steel. And so we went out and started our experiment. For fun, we made a smiley face on this plate of carbon. Then we shot more. We were sure to make a slow-mo video. We also wanted to see how many jugs of water it would take to stop a bullet. However, our calculations require a yield strength for the material, and water doesn't have a yield strength, so we just shot it anyway. It turns out that it takes 3 water jugs to stop the bullet that we were using. We found it within the 3rd jug. Since the bullet didn't penetrate through the 3rd jug, we decided to estimate that it was about 0.4 meters, or a little bit over a foot. Later, we examined our materials and found some cool stuff like how small this entry hole is for the rubber compared to the other materials. Later, we cut our materials and then sat down and took some measurements and really looked at what we had in front of us. So after we sat down and took our measurements, we noticed something. Our measurements were off by a lot. So we sat down and studied our calculations, and we thought of variables as to why our calculations were off as much as they were. As much as I'd hate to admit it, we had some relative discrepancies that were at least 50% or higher. The problem was that we neglected so much, our calculations were no good. So we were hoping we could get away with just this equation, with the one we started with. But really, for the situation we have, we need to take into account a lot of other forces. So here's the equation that we should have used. X equals 2 times x sub c times the natural log of muzzle velocity over the theoretical velocity. X sub c equals the mass of the projectile over the area of the projectile times 1 over the drag coefficient times the target's density. We didn't need to calculate the drag coefficient because somebody already did that for us. Now, that theoretical velocity is where the material strength forces equal the dynamic forces of the projectile. That theoretical velocity is hard to calculate. It's different with every material. We tried calculating it, but every time we would plug that answer back into the equation, we'd get the wrong answer for the distance. But since we already had our distances, we figured we would use this and solve for the theoretical velocity. Professor Cooley taught us how to make great spreadsheets, so we put that knowledge to use. So to solve for the theoretical velocity, what we did is we set up our equations so that the equation would run off of the theoretical velocity with all the other variables being the same. Then we would just drag it down, and we were looking for the same distance that we found in real life for that material. Then once we found the corresponding distance that we had in real life for that material, we looked at the beginning of the row and matched it up with the corresponding theoretical velocity. Yeah, we had that many calculations. And once we sorted through everything and picked out our theoretical velocity that matched up with that distance, we plugged it back into the formula and we got great numbers. It was the missing piece to our puzzle, and now that we had it, we were able to get great calculations. Our relative discrepancies were phenomenal, especially compared to the previous ones. So using this equation, we are able to calculate how far a bullet is going to penetrate a material. But, of course, it would only work if we had all the variables. I'm going to try to leave a link in the description of this video to the spreadsheet. I'm also going to leave links to our sources that we used to make this experiment happen.